So in this video today, we're going to be going through the SST electronics paper. Um, my friend Jovia has done this paper, so I'm going to go through the paper for him and mark it lah, basically. I highly recommend before even watching this video, you find this paper and then you do it yourself before watching. So okay, let's go. Alright. Okay. Complete figure 1.1 by drawing a line from the description to the correct symbol. Okay, I'm not gonna full screen. Because in the previous video I actually did not have an answer key, but this time I do. So I may refer to this sometimes. Okay, so this is 4 marks. What the heck? Momentary signal. Okay, I'm not gonna talk a lot about this because it's pretty much, yeah, it's pretty easy. Yeah, you get 4 marks for that. Complete table 2.1 by converting each component value. Okay, so nano is times 10 to the power. Okay, yeah, it's times 10 to the power minus 9. Not micro. Milli here is times 10 to the power minus 3. So let's see if he got it right. No, you got it wrong. Wait, so you haven't checked it? Okay, alright. So what's going on with this, bro? Okay, so that's wrong, and then this is okay. So how you should go about doing this, right, is for nano basically means, right, now your decimal point is here. It is now asking you to go to the left 9 times. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So now decimal point is here. Then we have this. You can do this, or you can put it in a calculator. I'm not gonna go through how to do it in a calculator, but yeah, this is it. And then you'll see that this is correct. So you don't get this right. You get 1 mark. Okay. Okay, this is just looking at the resistor value thing in front, so I'm not gonna show how to do this. But you are right. Yeah, you're right. Technically they didn't ask for. Okay, no, it's fine. Yeah, alright. Shows a wire wound resistor. Yes, more expensive. Okay. Such as a possible situation where it's necessary to use this. When a power rating greater than 2 watts is necessary in the circuit. That is the fact that you stated 2 watts. I mean, I would have preferred when a power rating greater than the normal power rating of a cheaper current resistor is necessary in the circuit. I would have went for that. I would have gone for that. In higher power applications, yeah, that sounds even better. So I will give you the mark. Shows an RC circuit that's used to create a time delay. To use a delay to allow a door to be open for a set period of time. Okay. When the door is closed, this will be like this. When it's open, it will be like this. And then calculate the time delay. So yeah, the time delay, which is tau, is just R times C. So if you calculate it right, then yes. So you got this one. Explain how R1 and C1 creates a time delay. It takes time for C1 to be charged, and R1 limits the current going into C1. A greater value of C1 would result in a longer time to charge. A greater value of R1 will make it slower to charge C1, which will also result in a longer time as well. I think I'm fine with that. Yeah, okay. You get both marks. Suggest a reason why a low resistance resistor is used for R2, and you just didn't do it. R2. I would say to make it charge quicker. Oh, to allow it to discharge quickly. R2. To allow it to so specifically allow it to discharge quickly. Interesting. Yeah, sure, okay. On figure 4.2, draw the waveform for the output of X when the door is open. So it'll be in B. Right, the door is open, yeah, it'll be in B. So, okay, the output of X. The output of X is just going to be the voltage across the capacitor. And we know that the capacitor will be discharging. So, what? So, yeah, the graph. What? Oh, whoa, whoa, what did I just say? Oh my gosh. When it's in B, it will. Did I just say it was discharging? No, the capacitor will be. Okay, Control Z is not working. What the heck? Um. Okay, hold on. Like a lot of my markings just disappeared. Okay, anyway, yeah. So Javai, you're just wrong. This is wrong because it is obviously charging. I don't know why I said what I said just now, but it's obviously charging here. So this is a discharging graph. So it should be It should be charging. It should be charging. And then even if it was discharging, it does not discharge to 0 volts after 4.7 seconds, which is 1 tau. It will discharge after 5 tau. So what? Anyway, they do they in and also you must state what's the voltage or I suppose what is going on, bro? This software sucks. I'm switching to Kami next time, bro. So you must also state the voltage after 1 tau and after 5 tau. They don't do it. Okay, well, they don't do it in. They don't do 5 tau in here, but I guess it would be better if you did. And you can calculate. Okay, and you can calculate how much tau will be at, because we know that for charging, when 1 tau has passed. Okay, let me get my calculator first. When 1 tau has passed, right? Around wait, what? Wait, Jovia, is it after 1 tau for charging it is 1/3 or 2/3? Okay, I can actually just search it here because I have the textbook here. So basically, okay, there's a video for you to watch for this, right? But basically, right, after 1 tau for, okay, everything is lagging now. Okay, so it's 2/3, yeah. So after 1 tau, um, the voltage across the capacitor will be 2/3 the applied voltage. So we would know that after 1 tau, the voltage will be 2/3 times the applied voltage, which is 5. Wait. Oh yeah, when n is 3.3. Yeah. And then after 5 tau, it'll be 99.3% of the applied voltage. And then you can just do the same calculation. This is very easy lah, so I'm not gonna go through it deeply. Okay. Rectangular, yes, this is rectangular. Signal oscillates between 5 volts and 0 volts. That is. No, this is wrong. Explain why the signal is periodic. It oscillates between high. Yeah, but this. let's say this is not a periodic signal, but it oscillates from 5 volts to 0 volts. So that means this statement is wrong already. The signal repeats itself at a regular interval. Yeah, there's an observable pattern here. You have to state that there's an observable pattern that constantly repeats itself. Okay, anyway, frequency. This is in microseconds. Oh yeah, so this basically means that each interval here is 250 U seconds. U is micro. Okay, just know that U is actually micro. Some notation will have it like this. So frequency is 1 over the period, and we can see that each period is around here because it repeats. Yeah. So yeah. So it will be 3 of 250 microseconds, which is this. Then if you calculated it right, yeah, you do get it. So yeah, this is correct. Calculate the duty cycle of the signal. So duty cycle will be the time it's on versus the entire time of the thing. So it is on for 2 intervals, which is 550, and then the entire period is 750, and then you just get a percentage, and then it's this. And you got that right. So yeah. Okay, 6.1 shows circuit of a half-wave rectifier. State the function of a rectifier to convert an AC signal to DC. Yeah, okay. Complete figure 6.2 to show the output voltage of this. And it's using an ideal diode. So this is correct. Okay, wait. Yeah, exactly. I. Oh my gosh, man. You get 0. So, guys, basically, right? Um, we know that AC, right? Let's say this is an AC graph. It goes from positive to negative, right? So positive, let's say positive is this way. Let's say it's this way. Then current can flow because of the diode. But if it's negative, okay, this software is actually bad. I can't use this anymore. If it goes this way, it can't go here. So there will be no output. That's why. Okay, I go into further depth into this in my half-wave rectifier vid. But basically, there wouldn't be a waveform when the input voltage is negative. So this is wrong. 7.1 shows a voltage regulating circuit 5 that provides 5 volts. Technically, it provides 5.1 volts. So okay, anyway, the key component of the circuit is the Zener diode. That's true. Okay, 7.2, which is this, sketch the IV characteristic graph of the Zener diode and label the Zener voltage. I would have preferred if you had done this. Like if, oh what? I would have preferred if you had drawn a line. And then now I can't move it. Is this stuff in England, bro? if you had drawn a line and then said VZ, but I'm giving you the mark anyway. 2 marks. For that is stupid, bro. Calculate the current through R1 when a load of 300 ohms is used. So that means, yeah, okay, that means this is 300 ohms, and then we want the current through here. So, yes, first thing I've done is this, I equals V over R. So we just need the resistance of the resistor, which we have, and we need the voltage across that resistor, which we don't have. But we can find the voltage because due to the nature of a Zener diode, we know that the voltage across the Zener diode will definitely be 5.1 volts no matter what. If you don't understand why, I'm not going to explain it here, but if you don't understand why, you can watch my video on Zener diodes. Just know that the voltage across this diode is 5.1. So using KVL, we know what's the voltage at R1 already because the voltage across this and the voltage across this has to add up to 12. So we can just do 12 minus 5.1, which he does and gets 6.9. So then he's just plugging in and then he gets his answer 31.4 milliamps, and that is right. So 3 marks. Okay, Table 8.1 shows 3 number systems to show the decimal value of 29 written in the other number systems. Okay, so let me just see if you're right, and you are. 2 marks. So to get this right, you can just use the calculator method, uh, which I showed, or I have videos on, so you can just go ahead and watch that. I'm not gonna go into too much depth of this because time is of the essence. State what the initials of BCD stands for, binary coded decimal, yes. State an advantage and a disadvantage for storing information in BCD. Okay, so the advantage is easier to interpret, but the disadvantage is it requires more bits to store and display. Correct. And display. Yeah, no one. I don't. Okay, no, it's fine. 2 marks is fine. Okay, so we got a logic gate. Complete 9.1 to show the truth table. So it's a NAND gate. Yeah, this is just memorizing, bro. Boolean expression for this. Yes, it's a universal gate, as it can be used to create the functions of other logic gates. Unclear. Unclear because the AND gate can also be used to create the functions of other gates, right? But you just need like a NOT gate or whatever to make an OR gate. You must state, okay? You must state that it solely can be used. It does not need anything else. You must state that. Okay. Once I'm done with section A, I'll tell you the marks first. 10.1 shows an example of a Gantt chart. State a benefit of using a Gantt chart in planning an electronics project. It ensures proper communication and monitoring of the progress of an electronics project. I don't see anything wrong with that. Proper communication, monitoring the progress. Okay. When testing the prototype, several types of test equipment can be used. Digital multimeter, okay, wait. Function generator, it produces AC signals of various types. Yeah. Digital storage oscilloscope, to observe how different points of a circuit changes with time. I mean, if the answer key accepts that, then displays waveforms of signals. Produces different types of waveforms, should be signals. I think I'll give you the mark. Okay, that's it. Okay, I'll tell you the marks first. Okay, so you get 4, 1, 1, 2, 2, 1, 2, 2, 1, 2, 3, 2, 1, 2, 1, 1, 1, 2. So out of, okay, 31. So out of 40, I think you got 31. That's not too bad, I guess. Alright, next. Section B. Okay, I think I went too far. Okay, section B. Factory decides to build a warning system when the temperature of the factory floor goes above 37 degrees. So then a warning light will be lit. Okay. Thermistor resistance chart. Explain why the thermistor is considered an input transducer. It converts temperature and analog signal to electrical signals. I think that's fine. Yeah, that's fine. What's the resistance at 37 degrees? Yeah, that should be easy. Yep. The thermistor is used to build this circuit that acts as a temperature sensor, as shown in this figure, and then acts as the output voltage. What is this? Is a voltage divider, yes. R1 is adjusted until the voltage X is 4.5 volts when the temperature is 37 degrees. Okay, so State and explain how the voltage X changes when the temperature falls below. As temperature falls below 37 degrees, the resistance increases. Applying the voltage divider formula, the voltage at X will become smaller. It's 3 marks though. What question are we at? The resistance of the thermistor will increase. Okay, you're right. Why is it 3 marks? Okay. Yeah, this is good. If you're to understand how to explain, basically Jovaya has used the method that I suggested in one of my videos very, very well. So writing the formula will be better. Yeah, okay. So if you want to learn more about how to answer the questions in this way, right, that I suggest, you can watch a video on it. I have a video on it. So yeah. It's just a pin diagram of a voltage comparator. Using this info, complete this circuit diagram. LED should light up when the temperature goes above 37. Temperature sensor circuit from 11.3, which is the voltage divider. A means of creating a reference voltage of 4.5 volts. IC supply connection. I mean, no freaking crap, right? Okay, so okay, 1 point should go to each thing lah. So I will mark IC supply connection is definitely there. And they didn't ask you to connect this, so I guess I'll give that to you. Did they? Oh, they connected it here though. They connected it here though. You know, it's fine. It's fine. A means of creating a reference voltage of 4.5. This voltage divider creates 4.5 volts. Okay, a trick for voltage dividers, right, is pretty much just ratios. So if you have the same resistance like this, right, it'll just divide the supply voltage in half. Temperature sensor circuit from 11.3, yes. And the LED should light up. Yeah. Yeah, okay, and this is in positive, right? This is negative. Okay, no, that's fair. Yeah, okay, 4 marks. Table shows a few parameters for the LED. LED produces the desired brightness when it's 20 milliamps. Okay, so we're looking at 20 milliamps. Graph extracted from the datasheet of the voltage comparator. Based on the chart, the low level output voltage at pin 7 is 0.37. Okay, close to ground but not really. When a current of 20 milliamps. Okay, using that info, calculate a suitable resistance value of R2 so that the current current of 20 milliamps flows through, and then you just didn't do it. Why didn't you do it? R2 eh? Okay, I'm gonna do it and then let's see what happens. So R is equals to VI, right? We know, okay, so we need the voltage across the resistor, and that would be that would be pretty much the supply. Okay, KVL again, right? Now we have 3 components here, okay? We have this battery, we have the resistor, we have the LED. I love this software. And then we have this thing that is close to 0 volts, but it's not 0 volts. It's a 0.37 volts. And then using KVL, we know that this is equals to this plus this plus this. So we just, to find the voltage here, we just take this minus this and this, and then we'll get the voltage there. And we know the supply voltage is 9, I think. So 9 minus the fall voltage of the LED, which is 2 volts, and then minus 0.37. Then we need the current, and we know that the current is 20 milliamps already, because we want the current to be 20 milliamps, so we're just going to set it like that. And if I plug this into a calculator, 37, right? 0.37 divided by 20 milliamps. Oh, okay, when you're doing this, right, you must don't forget to convert the prefix, huh? So I get 300. I get this exact value, and then let's see if okay, they rounded it down to 330. But I mean, the fact that it's an exact value, right? Then because it's an exact value, I wouldn't think you need to round it. So just keep it like this is fine. Show that the LED has not exceeded the maximum power dissipation, which is 100 milliwatts. So yes, we know. Okay, you're wrong. We know that the power is V times I. We know that the voltage across it will be 2 volts, and we know that the current is 20 milliamps. So we just plug this into a calculator. Okay, but in the actual thing, right, when you're converting the prefix into nothing, please show the conversion. Okay, I'm just not doing it here for ease of my life. So we get, oh, I love this software, 0.04 watts. And in terms of milliwatts, right, that is 40 milliwatts. Yo, this is the best software on earth. Whoa, ooh. Okay, so this is 40 milliwatts, which is lesser than 100 milliwatts. So this shows that the maximum it does not exceed the maximum power dissipation. And then if you want, you can write a statement below. Therefore, the LED has not exceeded the maximum power dissipation when a current of 20 milliamps flows through it. Or you can do that if you want. Okay, shows a system diagram for a cooling fan. 5-5 timer, damn. By referring to the pin connection diagram of the 5-5 timer IC, which is here, complete the thing. Yeah, complete the diagram. Such that this works as a monostable multi-vibrator. Oh wait, I forgot to check the answer for this. Yeah, I'm right. So monostable. Yes. Pressing this will trigger yes. R1, the resistor and can determine the duration. Yes. The IC supply connection is correct. Yes. So 3 marks. Yep. Calculate the value of R1 such that the motor will turn for 3 minutes. So you can use the equation for this. We can use this equation which calculates the period of like the on signal for monostable 5-5 timers. So you just plug it in and we can find R lah. So if you're right, if you didn't like mess up your calculation, which you didn't, then you'll be fine. So you are fine. Using the value, I'll choose a suitable resistor from the E24 series. So let's see if you're right. Okay, I'm not gonna explain why or how he did this. You can watch my ECF video. Yeah, not ECF. You can watch my E24 series video. Yeah, I explain in much greater depth. There's no point in going through it now. Okay, draw here the waveform of the output. Yeah, I mean it's pretty simple. Explain why the DC motor could damage the transistor. This DC motor will produce a large negative voltage spike when turned off. You put the decimal point wrong. Oh. It's fine. I know what you meant. Oh yeah, if it sounds like I'm schizo right now, right? Jovai is messaging me through WhatsApp. That's why I'm like, sometimes I'm talking to no one. I mean, I am talking to no one right now, but okay, no, it's fine. This DC, yeah, they can't see. The DC motor will produce a large negative voltage spike when turned off. So what? Which could damage the, yeah, I know. You have to state, so what? So what if you get punched in the ribs? No one cares. Oh, when you get punched in the ribs, you get hurt. Oh. Yeah, you have to state that you will get hurt when you get punched in the ribs. You can't just say that getting punched in the ribs is bad. You have to show with proof. Or you have to state what will happen. You have to state the impact, basically. Okay. Draw a diode on here to prevent that. So this is a flyback diode, and that's correct. 2 marks? Are you freaking serious? Okay, transistor has a saturation voltage of that. Okay, calculate the voltage across the motor. I don't know, man. It's probably super easy. It's 1 mark. So VCE set is 0.2, and then calculate the voltage of the motor. So that means this is 0.2. So all we have now is just simplification. Now we have this motor, and then we have a component that takes up 0.2 volts. So the answer is 9 minus 0.2, bro. That's it. There, 9 minus 0.2. Calculate the IC when the transistor is fully saturated. So yeah, this is just almost lost shit. Did you get it right? Yes. Okay. To drive the current IC, okay, the base current needs to be 5.2 milliamps, and then we can get the gain. So we know gain is C over B, or the current at the collector divided by current at the base. So again, it's just maths. Yep. Okay, 13.1 shows a system diagram of a counting system. 0 to 99 and then reset to 0. When this is pressed, the count will increase by 1. When this is pressed, it will reset. Okay. Just basic circuit analysis, right? This literally tells me... Okay, no, nothing. It's fine. State the pin number of this. So, yeah, 1, 2, 3, 4, 5, 6. At a particular instant, the output of pins A, B, C, D are 1010, and then state the decimal number represented. A is the least significant bit. A is a trick question. A is the least significant bit, which means that in binary, it's not this. In binary, it is this. So it's 5. You're wrong. Freaking hell. Yep, okay. This has a falling edge trigger input, but the clear input does not. Explain how this causes a difference in how they work. This will only change when a high decreases to low. This would change regardless of low increases to high, or if it's a gradual increase. Yeah, okay, acceptable. Wait, how much was this? 1 mark. Ah, that's a shame. 13.3 shows the photo and symbols of a single pole dual throw button. Yeah, C, no, and NC. Common, normally open, normally closed. Yeah, this is in the relay video. Contact bounds is a thing, which is removed using NSR Labs. Yeah, and then show that this. Okay, hold on. It's normally open or normally closed. It's normally closed. As in, like, this is normally closed. So that means this would be R. So this would be Q. And then yeah, so this should be right. Oh, you're wrong. Oh gosh. Oh, why did you do that? What's the point of doing that? Why did you do this? What the heck? So that means this is R, this is S, which would mean that this is S and this is R. So you know what this means? That means normally, because it's normally closed, normally you will be setting the value to be 1. And then when you close it like this, you reset it. So the function is entirely wrong already. You get 0 marks. 13.5 shows an incomplete circuit for the counting section of the system. Complete this power supply connections to this. Yeah. Single pole, single throw, push button to reset both counters. Whoa, they're making us check back. Why they so mean they don't show the circuit things? So you connected it to 2 and 3. Yeah, but this is a SPDT switch. They asked for SPST, so you got this wrong. Connections from the outputs of this to the two of them. This will display 10s, yes. This will A, B, C, least significant. Yeah, this is right. And this is right, yes. Connection that allows carry forward between the 1s to the 10s. Your what? Why are you connecting the 1s to the clock? Shouldn't it be the 10s? I'm wrong. Oh wait, no, that's the. Oh my gosh, this is the. No, you're wrong. You never connected the switch, so you're wrong. Yeah. Right. No, okay, wait. They were asking for carry forward between the 1s to the 10s. But there's no carry forward here. The carry forward would have to be from here to the clock, which is somewhere here. Yeah, I'm right there. It's connected from here all the way to the clock. So you're wrong. For 14.1 shows a production line, and they're counted because, yeah, okay. Okay. Shows a circuit, yep. Still one difference between an IR diode and an IO photodiode. IR diode is forward bias, photodiode is reverse bias. Yep. Still explain how the voltage at pin 2 of the comparator changes when the product moves in between the IR. Okay, pin 2. Okay. How do you explain it? The voltage at pin 2 will be 0 when a produce moves in between, as there'll be no current through the photodiode due to arrays, yeah. Then what if when it's not blocking? Why didn't you say that? You only say when it's blocking. Wait, what's the question? Alright, you get it this time, but I would have marked you. I would have marked you like 1. I would have given you 1 mark. Oh, I am marking. Okay. So the viewer, is up to you to decide whether he deserves this or not, but I don't really care. Still a function of P. So yeah, it's a potentiometer. 14.1 shows the truth table for the octal counter. Complete this with the Boolean expression for each one. Okay. So this is correct. And then K-map. So draw a K-map using that info. I'm lazy to do it myself. Oh, frick. Yo! Yo! So, this is just entirely wrong because we took it, me inclusive, as A. This software is so freaking good. A, B, and C. But actually CBA. So, everything here will be wrong. Okay. State the fully simplified Boolean expression of the K-map. So this will be wrong lah. Yeah. Okay, so the correct answer for this then would be A, B, C, A, B, C, am I right? Yeah, I forgot I have to actually explain things and go through. Yeah. So then your K-map would now be, would just be like this. So then you would group it like this. Then you would group it like this. And then you would see that these two are common, or C is redundant. So you would get A, B, and then you would see that B is redundant, so you get A. If you have no idea what I'm talking about, again, there's a video. So then this would be simplified. Yeah, and you can also show it like this. Yeah, so you're wrong. And then this is probably wrong as well, right? Alright, okay, end of paper. Finally! Okay, so let's see how much you did. Yeah, section B, not really good. Okay, so 1 plus 1 plus 1 plus 3 plus 4 plus 3 plus 2 plus 1 plus 1 plus 2 plus 2 plus 2 plus 1 plus 2 plus 2 plus 1 plus 2 plus 1 plus 1 33. Oh nah. Okay, 33. So I missed 1 mark. Okay, did I miss exactly 1 mark? Are you sure? Okay, so then you get 34. So that means 65. So that's a solid B3 lah, I think. Yeah, okay, that's it. So thanks for watching, I guess.